In this video, I'm gonna discuss about LC step response. In my previous circuit and systems video, I derived the LC source-free response, the mathematical expressions in both time and frequency domain. Today, in this video, I'm gonna talk about the step response of the LC circuit and derive the equations. So let's get started. This is the typical series LC circuit. So this is the series LC circuit. This is, say, input DC input Vs, and we're gonna apply KVL and KCL. So KVL IT. So in time domain analysis, so in time domain analysis, every single variable will be function of time. That's the analysis in time domain. So this is an LTI system. It will generate linear differential equation with constant coefficient, and so by KVL, so L d by dt plus 1 by C integration dt it, which is equal to the input voltage. So Vs, this is the magnitude of the input voltage for current through the inductor, voltage VL for current through the inductor, voltage across the inductor is VL equals L d by dt I, current through the inductor, ILT. This is the expression for voltage across inductor, and the current across the capacitor is IC, which is function of time. This is also function of time, which is C d by dt V, voltage across the capacitor. This is the expression. Now VCT equals 1 by C. If this side is differentiation, then the if we take this differentiation to current, it will become integration ICT dt. So these are the two expressions we're using. So basically VL plus VC equals the input voltage. Okay, this is the KVL, and which gives us this. Now what we're gonna do is we're gonna replace this differentiation and integration by linear differential operator. So d by dt equals d, and integration dt equals 1 by d. So using the differential operator is convenient for us because it gives us all the advantages of linearity property. Okay, so it is very advantageous and convenient for us to use the linear differential operator. We can get the answer from the differential equation very easily. So by linear differential operator, so L d plus 1 by CD IT equals Vs. If we further rearrange this, 1 by CD LCD square plus 1 IT equals Vs. Now LCD square plus 1 IT equals VSCD. We have got our current equation. Now we are gonna find the voltage equation. So by KCL, so let us assume that this is the ground, this is a node A, and this is node, say this is this is also a node. So at this node the node voltage here is Vs, and here the at node A the voltage is Vt. So say the current is coming through this to the node, and here here the current is going away from the node. So at node A here IL, current through the inductor, is equal to current through the capacitor IC. You can, this is obvious, current is uh, going into the node A, and IC is going away from the node A. So this is the basic equation. If we apply the KCL in this series LC circuit with step input or DC input, so this gives us for the current through the inductor, it is Vs minus Vt by LD equals C d by dt Vt. If you don't understand what I did here, I just applied the equation for the um, inductor. So we already know that current through the inductor is L d by dt V, sorry, we know that voltage across the inductor is LD by dt I induct current through the inductor. So this voltage is nothing but, for this case, this VL, voltage across the capacitor, is the difference between the node voltage Vs minus the voltage for the equation equals L. Let us replace this by differential operator. So LD ILT, which is ILT equals to Vs minus Vt by LD. This is the expression we are using here. So now that we have found the expression for the, by applying KCL, the full expression, let us just rearrange this. So Vs minus Vt, the voltage for the equation, equals LCD square Vt. Now just rearrange this again. LCD square plus 1 Vt equals Vs. So this is the, say this is number 2 and this is number 1. So we have got our two equations. All we have to do is solve them. So these are our two equations. Now let us find the transient response. For that we have to find the complementary solutions, and so characteristic equation of this LTI system, characteristic equation is LCD squared plus 1 equals 0. This is the characteristic equation, and it will give us the complementary solutions or eigenvalues for the LTI system. So here d equals minus 1 by root over plus minus j LC plus minus j omega n. Let us define omega n as undamped natural frequency of the LC circuit, which is 1 by root over LC. So transient transient response is, say we here I'm gonna solve for the voltage first, and because voltage is the principal response for the series LC circuit, and if I have to, I will find the current response. So the transient response equals C1 e to the power j omega nt plus C2 e to the power minus j omega nt, which is, if we use Euler's formula, which will eventually give us C3 cos omega nt plus C4 sine omega nt. So this is our transient response with arbitrary constants. Now we have to find the particular integral part. So for particular integral part, which will give us the steady state response of this series LC circuit with this input. So Vt, say steady state equals Vs by LCD square plus 1, which will give us Vs by D square plus 1 by LC, which is basically V, so LC, Vs by LC, and this is just, if we factorize this, and 1 by LC is omega n, so 1 by D plus j omega n, D minus j omega n. So if we write this cleanly, so V by, so V is the magnitude of the DC input, so Vs by LC, I'm gonna take the partial fraction of this factorized term. So say a by d plus j omega n plus b by d minus j omega n. So we have to find a and b. So here 1 equals to a into d minus j omega n plus b, sorry, plus b into d plus j omega n. So all we have done is we have equated this and this term and multiplied these two terms by this denominator, and we which leaves us with this. Now say d is minus j omega n, which will give us minus 1 by 2 j omega n. If d is plus j omega n, it will give us b minus plus 1 by 2 j omega n. So just plug the values. C minus 1 by 2 j omega n d plus j omega n plus 1 by 2 j omega n d minus j omega n. So here it will be 2 j omega n LC minus 1 by d plus j omega n plus 1 by d minus j omega n. So to solve this, we're gonna use a formula which is, so if d minus a x is the term for finding the particular integral, so it will be written in this form. So e to the power a x, assuming d by dx is the differential operator, 1 by d e to the power minus ax x. This is the basic formula. We're gonna use this here. So v is by 2j omega n LC so minus j omega n t. So 1 by d is integration e to the power j omega n t dt plus e to the power j omega n t integration e to the power minus j omega n t dt. So if we just integrate this, so Vs by 2j omega n LC minus e to the power minus j omega nt cross e to the power j omega nt by j omega n plus e to the power j omega nt cross e to the power minus j omega nt by minus j omega n. So this will cut out, leaving us with Vs by 2j omega n LC minus 1 by j omega n minus 1 by j omega n. So this is Vs by 2j omega n LC cross minus 2 by j omega n. So these two cut out, j and j will be minus 1 and minus 1 will cut out, and it will leave us with Vs. Say, so we know that omega n is 1 by root LC, so omega n square is 1 by LC, so omega n square, this LC term is omega n square by omega n omega n omega n is square. So this will cut out, so this will leave us with positive DC value, which is the steady state response. So complete response V, the voltage is C3 cos omega nt plus C4 sin omega nt plus Vs. Now what's left for us is to find the arbitrary constants. So we are assuming initial voltage across the capacitor and initial current in the inductor. So voltage at t equals 0 across the capacitor is Vo equals C3 cos 0 plus C4 sin 0 plus Vs, which gives us C3 equals Vo minus Vs. We know that current IT equals C d by dt Vt. So we're gonna use this fact, current, say current IL. So, and this is the voltage, so voltage response. So C, so this is not only the current through the inductor, this current is also going through the capacitor also, so this is the loop current. Okay, so C, this is the differential operator, C3 cos omega nt plus c4 sin omega nt plus vs. If we just differentiate this, so c c3 minus c3 omega n sin omega nt plus c4 omega n cos omega nt plus 0. The differentiation for the dc, this is the obviously constant value, so its differentiation will be 0. So capacitance, so here let me write now, it equals 0 is initial current of the inductor, which is equals to c minus c3 omega n sin 0 plus c4 omega n cos 0. Cos 0, cos 0 or sin 0 is that t equals 0, so this is what it is. Now if we just write it here, so c omega n c4, which will give us eventually c4 equals initial current by omega n cross capacitance. So we have got our two arbitrary constants. C3 is VO minus VS and C4 is IO by omega n C. Now if we replace the arbitrary constants with the corresponding values we have found, so VO minus VS cos VO minus VS cos omega nt plus IO by omega nc sin omega nt plus Vs. So if we just rearrange this, VO initial voltage of the capacitor omega nt plus initial current in the inductor by omega nc sin omega nt plus Vs 1 minus cos omega nt. So this is the voltage response, the full response. So now if you wanna find the current, so I don't wanna do the whole calculation for this differential equation. I will just use the formula, which is it, the current response, which is equals to Vs minus the voltage response by LD. So if you observe this circuit, you will understand that the loop current um, through the inductor is um, Vs minus the DC input minus the voltage response by LD. So this is the formula. Now we can easily find the current response. So Vs minus VO cos omega nt minus IO by omega nc sin omega nt plus Vs 1, sorry, this is not plus, this is minus, so minus 1 minus Vs 1 minus cos omega nt divided by Ld. So here Vs will cut out, leaving behind only, so if we take the minus common out, L 1 by L, so 1 by d, this is this is integration. If you pay attention closely, we are using the differential operator e 0 cos omega nt plus IO by omega nc sin omega nt plus Vs cos omega nt this is will be minus Vs cos omega nt. Now we are gonna do by L VO by omega n sin omega nt minus IO by omega n squared c cos omega nt minus this is Vs, the input voltage magnitude, by omega n sin omega nt. Remind you, this minus was there from the beginning, so this integration of cos is plus sign and integration of sine is minus cos. Now, so if we take this inside the bracket, it will give us minus VO omega n L sin omega nt minus plus omega IO initial current omega n square LC cos omega nt, and this minus and this minus will be plus Vs by omega n L sin omega nt. So now this will cut out, so IO plus initial current cos omega nt minus VO initial voltage omega nL sin omega nt plus Vs by omega nL sin omega nt. So now if we write all the necessary components and write the complete response, it will look like, so in time domain analysis, the complete step response of the series LC circuit is both voltage and current, but voltage is our primary response, our main response. So cos omega nt plus initial current by omega nc sin omega nt plus v is input voltage 1 minus cos omega nt. And if you want to find the current response is initial current cos omega nt minus vo by omega nl sin omega nt plus vs sin by omega nl sin omega nt. So this is the complete response. I think there's a plus minus difference from the source free LC response with the input uh, response. Obviously the transient response has some um, plus minus difference, so I don't know, but this is the answer, and that's it. This is the complete response in time domain analysis.